G'day folks, a couple of weeks ago you would have seen our video on the RB/2J Frankenstein kind of billet engine, and we've been getting a lot of questions about what is billet and what are the advantages and disadvantages, and to answer that we have flown into Adelaide to visit Darren. G'day Darren, how you going mate?
Good, how are you?
Good, good. Alright, well this time we're on your own home turf, so tell us a bit about your background, and I suppose we'll have a bit of a tour as well.
Well, we started out back in 2000 at this location, and we started out building engines and modifying cylinder heads, and things just progressed from there. We put a CNC porting system in, and then we started making components, which evolved into making engine blocks.
Okay, alright, well to show us what is billet, that's a question we're getting a lot of, I guess we'll have a look.
Okay, let's go. So in this part of the shop is where we make the engine blocks. So these pieces of 6061 plate, so this is a 10-inch plate, and they're cut out of that plate into these smaller pieces.
So billet just means a block of solid alloy, basically.
That's right. So these particular ones are forged, so they're forged into shape and heat treated, and that's how they start out before they go into the milling machines to be carved into the shape of a block.
Cool. Alright, so I guess from here, where does it go?
Okay, so from here it gets mounted on a jig, and then we bring it over here to a machine. This is a 4G63 block being machined now, and that started out as exactly that piece that we just looked at.
How long would it take to actually go from that block to something that's recognisable as an actual usable engine block? So just the machining side of things.
Well, in this particular setup, it's in there for a day. So that's the upper part of the engine block as such, and then so that does 4 sides in that setup, and then we have to do the ends afterwards. So once it's finished that, then it will come out. So you can see here, this is another one ready to go in the machine. There's our jigs on the end where we mount it in the 4th axis. So once they come out, then we'll have a cradle as well. So this is another drag racing block with no water jacket. So we have a cradle as well, which is a separate piece that's been made, and both of them have these leftover scrap on the ends. So we assemble the block with the main studs, and then this will go mounted in the machine on its end like that, and machine this end, and then we flip it over and machine the other end, and then we end up with a finished piece. So you can see he's getting that ready there to go in to the other machine to machine the ends. Then once we machine the ends, then it looks like that.
And then from there, what happens after that? Do you put all the sleeves?
Then we put the sleeves in, so we heat the block up, and then we slide the sleeves in.
And that basically gives the strength that a cast block would have previously done, I suppose.
Well, the block itself is stronger than a cast block because of the way it's designed. And this is really for the cylinder, for the rings, the piston rings to run on, and so it creates a cast iron cylinder, the same as what you have with a normal cast iron block. And so that's a K-series block there with the sleeves installed, and that's in our sun and hone to be honed to suit the pistons for the customer. He supplied the pistons, so we'll measure these pistons up, and then we'll hone the block to suit, and ship it out to him.
So before it goes to the actual CNC machine, I guess you've got a computer that has that model on it. Can you show us what that sort of looks like?
So this is our CAD design office.
So that's what we were looking at in the machine just before?
No, that was an Evo.
Okay.
But this is the K series, like was in the home.
Okay.
Without a cradle. So yeah, that's one that we've modelled in the past, and basically what we're doing is we're taking this 3D model, and this software here, we use SolidCam, as you can see in the corner there. So SolidCam has SolidWorks embedded in it, and this is what we use to, it generates the toolpaths that tell the machine how to move to cut that shape.
Mm-hmm. So if you were to want to create a new engine, like let's say you wanted to make a 1J or something, do you take one out of a car and then, like, what do you do to actually create this model here?
Basically, we get the engine out of the car and have a look at how all the ancillaries are mounted, and then we have a bare block, an additional bare block, which we measure. We don't physically scan the block because the factory shape of the block is not really relevant to us. What we're looking for is to make sure that all these bores are spaced correctly, the head bolt holes are in the correct location, the distance from the crankshaft center line to the deck is the same as factory. You know, the length of the block, the way the bell housing is, all the critical dimensions is what we're capturing, and then we model the block around that using our designs to ensure that it's stronger for what it's going to be used to. So we have clients with 4 cylinders making above 2,000 horsepower, so it has to be designed in a way that it can withstand that level of load without changing shape. And so that's the key to it, is that you want a cylinder block, or in a lot of cases you want all the components in the engine to not change shape under load. That's how you're achieving, that's how you make maximum power.
Alright, so we've talked about what is billet and so forth, but why is it better? What are the advantages and disadvantages? Obviously we've got cast iron is what a lot of older cars come with from factory, and this is what you're ultimately building here. What are the advantages, disadvantages, and why would anyone want to go billet, and at what sort of point in someone's build is that kind of necessary?
Well, they've, you know, as everyone knows, with the 2J they make substantial power with the iron block, but it is a case of what do they have to do to the block to do that, and how long does it last after they've done that before it has to be replaced. So as you can see here with this 2J block that's been sectioned, this gives you an idea, and you can see especially here in this crankcase area how thin it actually is. This is the wall of the bore, which is still quite thin. It's your water jacket where all your water runs, and the outside of the block, and then this is the deck. So the deck thickness there is approximately 8mm. So the problem is that when the engine is put under extreme load, then it all moves, and if this was thicker it wouldn't move as much, and so the block would be more rigid, and then first of all you make more power. But the thing is when it moves, the material has a yield point, which means how far can it move before it breaks. So with cast iron, your yield is between, depending on the iron, how it's made up, it's between 1 and 2%. So if, you know, that means 1% of the, if it moves more than 2% of the thickness, it'll crack. Okay. Whereas aluminium has a yield of around 10%. So it can move a lot more before it breaks. The 606 aluminium, heat-treated aluminium, T6 aluminium, has a similar tensile strength to cast iron. So the actual strength of the material isn't much different. But what we do is then we make the block, the architecture of the block is in a way that is much thicker in all the areas you need to be. So around the bores it's thicker, our water jacket is shorter, which means that the bore has less distance of unsupported wall. The way like in this case it's a solid, so there's no problem with thickness there at all, but in a water jacketed one, the aluminium is thicker. Also, it's solid around the top for longer, so we don't, in these blocks the water runs behind here, which means all this is open, whereas with ours the water runs here, and so this is all solid and the bores are joined together. And in addition to that, here you can see you've got probably 4 or 5 millimeters of thickness through here, whereas our aluminium blocks are 15 millimeters thick through here. So that adds a lot of rigidity to the block, and it stops the block moving under load.
Okay. And what about weight? I suppose that's a big saving as well.
It depends
Maybe
on the
not
engine.
In this example, because this one's a drag motor. So.
Yeah, but it depends on the motor, because the 2J is actually quite a compact engine. So the deck height is short, and the block itself is quite compact for a 6-cylinder. So because we've added so much material to increase the strength, then the weight difference is only about 4 kilos on a 2J block. Whereas on an RB, which is a bigger block, we're at 30 kilos different. So, and again, even with a 4G, which is a 4-cylinder, much smaller engine, but we save 20 kilos on that. So we're up around 40% lighter on that.
Okay.
So, and the other advantage with the 2J in particular we do is you can see here's the main oil galleries. So that's where the main oil pressure feeds along the block to feed through here to all the main bearings. Now, as you can see, that's quite close there. So when you put an aluminium rod in the engine and you have to clearance here to so the rod doesn't hit the block, it gets quite thin. So that can be a problem. So what we've done with ours is we've moved these up. There you can see there that that's the original location. We've moved these up to get them out the way, so it gives us more material down there for rod clearancing.
At what point would you suggest to someone that, you know, cast probably isn't the answer? Because, I mean, for a 500 horsepower build, this would be well overkill. Is there a sort of a point where you'd sort of suggest, look, this is where you really need to start looking at billet?
Well, I think long term, if once you're above, well, with the 2Js, once you're above 1500, it's just a matter of time before the block's going to let you down. And again, it depends what you have to do. People are filling the water jackets with grout to try and make the block rigid. They're remachining the main caps and putting steel caps in to try and strengthen everything up down there, and putting girdles and all sorts of stuff on the blocks. So it does come down to how much do you want to spend. Do you want to spend $5,000 or $6,000 preparing an iron block to withstand the extra load, and then down the track it still lets you down? Or do you want to spend the extra and have something that will go forever?
And so, maybe not this particular example, but a 2J, I think it was around $10,000. Is that about? US,
yeah.
So you're not really spending a huge amount for the extra insurance, saying a few $1,000s more.
No, that's right.
Yeah,
that's right.
Are there any disadvantages to going like the billet block? Like for streetability, is there like temperatures and wear or anything like that?
Not so much wear. Probably the biggest disadvantage is having someone knowledgeable that can build the engine for you, because the billet engine is not something that's widely used in the industry. Even in the V8 industry, the billet engine is a small niche market. So there's only a handful, or like worldwide, there's only a few engine builders that have been exposed to it. Okay. So we have found that with some clients who have bought the engine and they've taken it to their engine builder who's assured them that they can do it, and then they come back and they've had some problems because they didn't really know what they were doing. So there's other things that you need to deal with. changing sizes with temperature and stuff like that. But it's nothing that can't be dealt with. It's just that you have to have someone with the experience to do it.
I happen to know someone that knows how to build billet blocks.
Do you?
Yeah.
So here's a wet 2J, similar to the one we just looked at. So if we section the front from the front, so you can see here, so this shows us the thicknesses there. So you can see.
And that's the oil gallery that you've moved, so it used to be down there, is it?
Yeah, so that's the main oil gallery on that side, which feeds the main bearings, and then on this side here you can see that's your tube coming down for where your oil squirter mounts, down the bottom there. And what you can see is, that's the aluminium on the bore wall, but remember then there's a cast iron sleeve inside that. Alright, so that's as thin as it gets, and then of course once you have a look down here in the crankcase you can see these wall thicknesses here. So if we come through, and then you can see there, once we get into where the head bolts are, you can see that it's all solid through there. That's your main oil feeds. There's your oil drains from the cylinder head, and also your bolt. So there's your threads for the head studs and the main studs, and you can see how deep they go and then how far below the surface the thread starts. So that's where the thread starts. This is clearance. So what that means is when you torque the stud up and it's pulling up, it's not distorting the deck, because the point is so far below the deck from where it's pulling from that it keeps the deck shape from distorting too much. You can see here we do all sorts of things, like this is the valley plate for the billet manifold that we just looked at, and then the rest of the manifold's still yet to be machined. So yeah, down here, over there you can see we have a balancing machine, the crankshaft balancing machine. Here's a rod hone for resizing con rods. Like this is an RB30. It's been CNC ported. So the 5-axis CNC porting is what we started out doing, and then moved on to making components. You can see we have a lot of cylinder heads there waiting. We've got an engine on the engine dyno today that's just fired up, so if you want to have a look in there. There's our engine room.
So it's going to be a little bit loud for this part of the video because those guys are busy. We don't want to keep up all their day. So what are those guys actually doing?
So yeah, that's an outside engine builder has brought his engine down to use our engine dyno. It's a small block Chrysler for a streetcar. So I think they're looking at high 600, 700 horsepower today. So we'll see what we get out of it.
Okay. We'll try and finish this before they start revving that up.
Yeah. So yeah, here's our engine room. So as you said, a lot of people don't realise that we build engines, but that's what we started off doing, and it evolved from there. So we have all sorts of different engines in here. We build all sorts of different engines. We're not just an import thing. So we have a billet SR over here in the corner.
Yep. Now are these for street applications?
This one is. Yep. This is a street car. That's still using an S13 cylinder head. This is another street car, so this is probably this is going to be about 1200 horsepower. This engine is projected to make. It's a billet RB 3.2 litre with our CNC ported cylinder heads on it. It has a dry sump. And then we have another one here, which is a similar power level, similar turbo. That's one of the earlier blocks. Again, our CNC ported head. So yeah, that's actually going into an LJ Tirana, that one. I mean, we even have a Holden 6 red motor here that we still do, which not something we enjoy doing, but we still do them. There's a small block Chrysler, ready, final clean, ready for assembly. Small block Chev, another street car. And here we have an LS1, this is actually a HMS engine. So we were contracted, the client came to us and contracted us to build a HMS engine for racing in super stock. So in this particular class, you have to use a factory cathedral port cylinder head casting and a factory block, and it's a weight brake class, so it's all about horsepower per cubic inch to be competitive. And with these types of engines, we need to make around 2.2 horsepower per cubic inch, and this engine actually it's a 329 cubic inch, and turns to above 9,000 RPM, normally aspirated. Then this is our Cyclone. It's a Renshaw product. So that's we have like a probe here that fits to that, and then this machine you set start and end points, and it'll follow a shape and it'll give you a point cloud that can then convert into a surface. So just basically we're going to take a complex shape and turn it into a digital model, so then we can bring it into the software and machine that shape. Here is a flow bench. So we mount cylinder heads on there. So a cylinder head sits on there, and then when we turn this machine on, it pulls air through the port, and that measures how much air is flowing through the cylinder head, which then we can use that to we work out the size of the port in different areas, what the airspeed is, how much air is going through there, tells us how much power we can potentially make with our engines. And so this is where we develop the port shapes before we scan them, make digital models, and then they go into the machine shop and we can machine them to replicate that shape. So you can see on that one there that's been CNC ported previously. And so still got.
So you can get the theoretical maximum, like if you take a factory head, put it in here, you can work out theoretically, if all things go right, what power that head can make out of the box. Yeah,
by changing the port shape and measuring the flow, that gives you, there's formulas that tell you how much power that head can potentially make, the engine.
Yeah.
There's a lot more to it to that, but because of airspeed, the valve size versus the bore size, there's a lot to it. Yeah. But basically that's where we're looking to try and develop the cylinder head to make the most power.
Back tested RB versus 2J head to see what flows better from factory?
Yeah, the RB head flows a lot better. Yeah. and then when you port them, the RB head still flows a lot better as well. So yeah, that's
just hurt me inside there.
You'll be all right.